So good morning, everyone. Welcome back to Math 115. So today we are going to talk about, actually we're going to do something a little bit different. We're going to finish section 2.4 and then we're going to have some group activities. So I'll talk more about that in a second after I remind you about your homework, which is due on Thursday, which is tomorrow. Thursday is tomorrow, so you have 2 homework assignments due tomorrow. I'm going to post 2.4b today. And your next assessment is not quiz 4 anymore. Your next assessment is the exam, which is going to be on Wednesday after fall break. Okay, exam 2 is going to be on Wednesday after fall break. It's going to be 3 pages long, and it's going to cover these sections, which I talked about last time. So regarding my office hours, actually, I was a little bit lonely yesterday. Nobody came to my office hours. I didn't know what to do with myself. So, based on my understanding of the class, I think there are some of you that probably could benefit from coming to office hours. So please do so. All you have to do is just get your body to my door. I'll take care of the rest, okay? I will find something for us to work on, find some way to help you, okay? So as long as you can show up, then you'll get the benefit, I promise. So that's office hours. My next office hours are going to be on Thursday. That's, again, tomorrow, from 2:30 to 4 in my office. Or if we have a lot of people, we'll move to a classroom. If you can't come to my office, but you still need that help, which some of you do, I know some of you do, go to the Math Tutoring Center, okay? Not trying to shame anybody. It's totally fine. I mean, we're doing pre-calculus at like a breakneck speed. Okay, especially if you're coming from high school, okay, it's going to be different. It's going to be harder. It's going to be faster. So if you need extra help, there's absolutely no shame in it. Please make sure that you're making use of these resources to get the help that you need. Okay, one more thing I want to discuss about our class is I've basically come to a decision that I'm not going to try to speed myself up in order to cover all of the possible topics that are in a pre-calculus course, basically, or in this pre-calculus course curriculum. It's just too much to do, and you aren't going to learn well if I just sit up here and motor mouth for like 90% of the class or like 95% of the class. So we had a really fascinating speaker in the math department yesterday, who was saying things that I guess I kind of already knew, which was essentially that, look, students learn better when they're actively engaged, right? So active engagement for students in the class, for us, with the way that our classrooms is set up, is mostly going to be partner work and group work. Okay, so what I want to do is allow you all to get your hands on the material during class when you can work together, learn from each other, and ask questions of me. So what I want to try to do is transition from what we're doing now, which is basically 90% me talking and 10% you doing work. I want to transition closer to like a 50-50. Okay, so what that means is the format of our class is going to change a little bit. What I'm going to try to do is give basically very short, compact 5 to 10 minute lectures, followed by group activities, okay? So that means I'm not going to go through as many full examples and example after example in extreme detail on the board, okay? A lot of that is going to get passed on to you doing it together and with my help as necessary, okay? So just bear with me as we transition into that. I think that it is going to allow you to learn things a lot better. It is going to make us go slower, but what I want to do is basically I want to make sure, okay, look, there's like a million different things in our curriculum. What I want to do is select the topics which are going to be most important for you if you move on to a calculus class. And what I want is for you all to master those topics so that when you get to the calculus class, you feel like you're well equipped, as opposed to just showing you 1,000 different things with very little detail and you don't learn them very well, and then you feel like you get to calculus and it just got harder, but you didn't learn anything in pre-calculus. You see what I mean? Okay, so that's what I'm going to do. What I'd like you all to do is monitor how you like it, see how well you're learning, and if there needs to be a change, then please let me know, either via email, or you can talk to me after class, or you can make use of the anonymous feedback survey, which is on Blackboard. So you can fill that out. You don't have to leave your name or your email or anything. You can just say, this sucks, or this is great, okay? And yeah, just let me know how it goes. All right, does that sound like a plan? Any questions? Okay, and any administrative questions before we start for today? Okay. One more thing for the group work. I know some of you like to or prefer to work alone, or else you're just sitting in a seat that's kind of isolated. I would like you to try to make an effort to join a group, and if you see somebody working alone, try to adopt them into your group, okay? So if you have a group of 2, you see someone working alone, try to adopt someone and form a group of 3, okay? All right. So if no questions, then let's start in on content for today. So I'll remind you what we talked about last time, which was more information about rational functions. And basically what we're doing is we're putting together like all of these different techniques for how to graph rational functions in a given region. Okay, so we talked about how to graph a rational function near a vertical asymptote. Okay, so we talked about when are we going to have vertical asymptotes? Where are they going to be? When are we going to have horizontal asymptotes? And where are they going to be? So now what we're going to do is incorporate also this information which we talked about last time about, okay, well, what is the behavior of the rational function near a 0? Okay? And then we're going to ask, what is the behavior of the rational function at the y-intercept, right? And then by then, we're going to know where is it positive, where is it negative, where is it 0, where is it getting close to as we go to infinity, where is it getting close to when we're around vertical asymptotes, and we're going to put all of this together to try to form the graph of a rational expression or rational function. So for the behavior of the rational function near a 0, okay, we just care about, well, the zeros of a rational function will be where the numerator is 0. So if the numerator is 0, then that means that one of the zeros is being plugged in for x, right? Namely a here. And then we ask, what is the behavior? Well, near that 0, it's going to look like a transformation of the function x to the m, where m is the multiplicity of that 0 in the numerator. Okay, so for this example, we had a multiplicity of 2 for the 0 x minus 2. So what does the function look like when x is close to 2? Well, the numerator is going to be close to 0, right? Because this number is close to 0, almost 0, right? So we take basically the rest of the rational expression and we just plug in whatever that 0 is, okay? We just plug in whatever that 0 is. And that's how we get the factor, which is going to be the stretch factor for our transformation of the function x squared. Okay, it's x squared, but it's moved 2 to the right, and it is stretched by a factor of 9. So when x is very, very close to 2, we see that the function basically looks like x squared. Actually, it basically looks like 9 times x minus 2 squared, right? That's what it looks like. So it should be stretched, right? So maybe x squared would look something more like this, okay? But it's stretched vertically by a factor of 9. And this is basically what we expect the graph to look like nearby 2. So what do I mean when I say nearby 2? What I mean is maybe in the graph, this would go from like 2.2 or like 1.8 to 2.2, something like that. So very close to the 0. This will be the behavior of the function. Is that clear? Okay, then let's talk about the next thing, which is the behavior of the rational function near a vertical asymptote. So roughly speaking, what I'm trying to decide is, well, if I have a vertical asymptote, is it going to look like one of the following things? Is it going to look like this? Or is it going to look like, maybe it looks like this? Or maybe it looks like up on one side and down on the other, or it looks like down on the one side and up on the other, okay? These are basically the four options that it's going to look like near a vertical asymptote, right? Because we know that the function is going to either plus or minus infinity. We just need to decide what's happening on each side. So that's where we're going, and that'll be basically the last thing we learn and until we're ready to graph altogether. So we can rewrite the rational function, okay, as, again, we factor out the relevant 0 in the denominator with whatever its multiplicity is, okay? And then you can rewrite this as n of x divided by q of x, whatever is like the leftover. This is the remainder when you divide the denominator by x minus a to the power m. So then we get this times what? Times, oops, I should have left that. 1 over x minus a to the power m. Okay, so this is basically a transformation of the function 1 over x to the m. Yeah, it's a transformation of the function 1 over x to the m, which you can decide whether that looks like, this, okay, or like this, basically, depending on what is the power of m. Okay, so depending on the power of m, that's going to decide for us whether we have same behavior at the asymptote or opposite behavior at the asymptote. And whether we have same behavior going up or same behavior going down, well, that's going to be determined by the sign of what we get when we plug in a here. Okay, so two things matter for the behavior of the rational function near a 0 for the denominator. Those two things are the parity of m. Okay, parity means even or oddness. Even or oddness. Okay, that's the parity. And then, of course, there's the sign of the rest of it. So those two things matter. The sign of the rest of it when we plug in a, and whether m is even or odd. So two things which can have two possibilities. So we have 4 total possibilities if we combine them all. And you can see this in the following table. Is it okay for me to scroll? Yeah, okay. Then this is the table of what's going to occur. Okay, so remember, we're talking about the function, which is, we know that the rational function is going to behave like n of a over q of a times 1 over x minus a to the power m. So let's ask ourselves what happens in the case when m is even and the factor is positive. Well, if m is even, then I hope you agree with me that the denominator of this fraction is always positive, right? Because whether we take a negative number or a positive number, we take it to an even power. If we take an even power of any number, it's always, always positive, right? So this number is positive, and so is the factor which we are multiplying by. So altogether, if m is even and n of a over q of a is positive, then r of x is definitely going to be positive, no matter what, right? It's going to be positive. So what is this function going to look like? It's going to look something like this, going up to infinity. Because we can't go to negative infinity. Why can't we go to negative infinity? Because if you take a negative number and multiply it with itself an even number of times, then it becomes a positive number. And a positive number times a positive number is still positive. So there's no way for the function to be negative near this 0. Okay, so that's option 1. Option 2 is if, well, which one should we do? Why don't we do go down. Okay, we're going to go down. We're going to say m is still even. But now we're going to say that the factor is negative. So what has changed? Nothing has changed about the fraction. The fraction's still a positive number. But now the factor which we are going to multiply it with is a negative number. If I take a negative number times a positive number, I get a negative number, right? So if m is even, we're still going to have same behavior on both sides. But since the factor changed from being positive to being negative, we're going to see the same behavior on both sides, but it's not going to be going up, it's going to be going down. Okay? So that's if m is even. If m's even, we go up on both sides or we go down on both sides, depending on the sign of the factor, n of a divided by q of a. Okay, now let's look at what happens when m is odd. Well, spoiler alert, when m is odd, we have opposite behavior. And this also is, it's nice because it's consistent with the end behavior, right? If we have a degree, an even polynomial, the ends go in the same direction, right? If we have an even factor in the denominator, or even multiplicity factor in the denominator, again, same behavior on both sides, right? So it's same behavior goes with even. Opposite behavior goes with odd, okay? So that's what we're going to see on the right-hand side. It's not going the same way, but going the opposite way. So let's see what happens if m is odd. If m is odd and the factor is positive, then we need to consider what's happening on the right side and on the left side. When x is larger than a, so let's just consider what happens when we plug in a number which is close to a on the right side. Then x is larger than a. So what kind of number is x minus a if x is bigger than a? Positive or negative? Should be positive, right? Take a positive number to an odd power. What kind of number do we get? Positive. So this number is positive. And if this number here is positive, which we multiply a positive with a positive, we get a positive, right? So on the right-hand side, we see that the value of the function is going to be very large and positive. So it should look something like this, yes? And you don't even have to check what's going to happen on the other side, do you? You know it's going to be the opposite, right? But okay, let's talk about it. If x is less than a, then x minus a is negative. If you take a negative number to an odd power, you get, again, a negative number. So if I multiply a negative number with a positive number, I get a negative number altogether. So it's going to be a negative number, which is really, really big, so it's going down to minus infinity, okay? And I'm going to omit the explanation for the other one, but you know what's going to happen, right? What's going to happen when the factor goes from being positive to being negative? It's going to not look like this. It's going to look like the reverse of that. It's going to go up on the left side, and it's going to go down on the right side. Okay? So two things that matter, right? It's that factor out front and the parity of the multiplicity. So whether the multiplicity is even or odd. That's what the word parity means. Okay. Any questions about that? Yeah.
They all continue in like the other direction too, right?
Yeah, so you mean like this way?
Yeah.
Yes, there will be something on the other side, but what I'm actually doing here is I'm not worried about what's happening elsewhere. I'm worried about the behavior of the function near x equals a. So when I plug in a number which is close to a, like a plus or minus like 0.2, something like that, then the graph is going to look like this, okay? It's going to look like this. So I only talk about what's happening nearby, okay? What happens elsewhere is who knows what, right? But that's what all of our other techniques are going to help us do. We're going to basically put together a handful of things like, oh, it looks like this here, it looks like this here, and I know that it has a horizontal asymptote over here, and so all together you're going to say, well, I feel like this is going to maybe connect here, and then this looks like well, we'd have to maybe bounce off and come like this or something like that, and we know that it should go up at the end. So we're going to put all these different pieces together in order to make the graph of the rational expression. So yes, I'm only talking about what the graph looks like close to A. So I shouldn't draw such long tails on these, should I? I should just make them shorter so that you can tell what's happening close to A. Okay, close to A. Any other questions? Okay, then we're going to talk about, finally, the 6 steps to graphing rational functions. And then we're going to have some group work. Okay, so I don't want you to write all of these down. I want you to refer to the notes later, okay? But here are the basic steps, okay? We have a handful of pieces which we are going to say, well, the graph of the function looks like this near this location, and we have maybe like 8 locations that we have a vague idea of what the function looks like. And then we're just going to play connect the dots. Okay, we're going to play connect the dots. So the first step is to find the intercepts, okay? That means the x-intercepts where the function value is 0, and the y-intercept, which is, we're going to find the x-intercepts, which is where the function value is 0, and we're going to determine the nearby behavior, you know, whether it looks like an even function or an odd function or what. And we're going to find the y-intercept, which is where we plug in 0, right? That's what we do to find the y-intercept. Okay, then we find the vertical asymptotes. We already decided how do we find the vertical asymptotes. Well, that's going to be where the numerator is not 0, but the denominator is 0, right? And determine the nearby behavior. Namely, we use the previous chart to determine should it be up on both sides, should it be down on both sides, should it be up, down, and if it is up, down, then which direction, right? So that's vertical asymptotes. Then we also need to find the horizontal asymptotes, right? Or if there are none, then determine the end behavior. Are we going up to infinity or are we going down to negative infinity? Okay, so those are the first 3 things. Then we're going to do the following. We're going to test for symmetry. Okay, we're going to test whether we have a symmetry about the y-axis, namely, is it an even function? And we're going to test for symmetry about the origin. Is it an odd function? Okay? Then, okay, if we have a horizontal asymptote, we need to determine whether we go to that vertical asymptote in one of 2 ways. Here's the first way that we can approach a horizontal asymptote. The second way we can approach a horizontal asymptote would be from above. Okay, so we need to determine that. Okay, and then finally, once we have steps 1 through 5, we're going to have like a good picture of what the graph of this function looks like in a handful of regions, right? And then we are going to fill in the blanks with a smooth, continuous graph. Okay, so a lot of steps here to do, okay? But basically, we need x-ints, y-ints, we need vertical asymptotes, we need horizontal asymptotes, and we need symmetry. Those are the key components of graphing a rational function. Okay, graphing a rational function. Okay? So, what we're going to do now is work in groups to try to put all of this together and get a reasonable picture of what this looks like. So let me put on the screen. We want x-intercepts and behavior. We want y-intercept. We want vertical asymptote and behavior. We want horizontal asymptote and behavior. And then, was there anything else? No, fill in gaps. Okay, so this is our process. So go ahead and get into a group. Your group could be maybe 2, but probably no more than 3 persons based on our classroom setup. And I'll be walking around and I'll try to stop by many different groups and see how you're doing as you go along, okay? Are there any questions before we start? Okay, then let's go ahead and get started.
And I was so exhausted at one point, I just I spent 3 hours doing it's not hard. I have to do an exam.
Okay, if your group gets a little bit stuck, just raise your hand and I'll come help, okay? Okay, so how about X-Intercepts, right? So we know if we have an X-Intercept, right, that we're touching the x-axis, which means that this point has the form, it's going to be some x value, but then do you know what the y value should be if we're down here on the x-axis? It should be 0, right? So what we want to know is what x values can I plug in the function and get 0, right? So I have a rational function here, right? It's a number divided by another number, right? If that rational function is equal to 0, then we know that the numerator has to be 0, right? If the whole fraction is 0, then the numerator has to be 0. So what we're looking at is we want to solve something like x squared plus 2 is equal to 0, right? This is the function that we want to solve, right? So how would we solve something like this? If we commit 2 over to the other side, we get x squared equals negative 2. And then backwards. Anyways, negative 2, right? Is that possible? Take a number, square it, and you get a negative number? No, that's not possible. So what do we think about X-intercepts? There are none. See what I mean? Okay, now let's work on the Y-intercepts. We know that Y-intercepts, it's not going to be the Y value that's 0, is it? It's going to be the other way, right?
So is this plug in 0 for everything?
Yeah. So that means it's going to be where all along the y-axis does it cross over. If there's no x-intercept, yeah, exactly. If there's no x-intercept.
Oh, it's negative 2. I think so. Wait, but
What matters for the horizontal asymptote? Yeah, the degree of the numerator and denominator, right? What's the degree of the numerator? vertical on the denominator also two, so the degree is the same, right? So the vertical asymptote is going to be 0 because the denominator is bigger, right? Because the denominator grows faster than the numerator, right? If they grow the same rate, they have something like
Well, actually,
if we're going to look at the leading term of the numerator, which is x squared, right? And then the leading term of the denominator is also x squared. Take those two, combine them, and equals over, right? So the horizontal asymptote is going to be 1 divided by 1.
No, you don't have to.
I think I was thinking of multiplies with 0 and it's like, that's why I kept like,
If you fold this out,
and it's less than that. Are they equal to each other?
so you multiply these out.
If you multiply them out. So, which means we're supposed to multiply that.
Well, there's vertical aspect, right? That's what we have said. Which when we have something like this, when the denominator is becoming 0, right? So when does the denominator become 0? It becomes 0 when x is -2 or when x is 1, right? So these are not going to be our x-intercepts. They're actually going to be the locations at which we have a vertical asymptote. Oh yeah. So let's talk about the x-intercepts, right? Roughly speaking, is where our function touches. If our function touches 0, then the function height is 0. So if I have a fraction, something divided by something else, and that's equal to 0, what must be true? Well, if I take 1 over something, which is there any number if I can divide 1 by? And make it 0? Well, no, I'm sure that's not fine, right? So, no, the number by 0. The numerator, something like 0 divided by 3, that would get us 0, right? Something like that. So we're looking for x-intercepts, which we know is going to be when the function value is 0. If the function is defined by a fraction, that means the numerator has to be 0. So what we're looking at is trying to solve is the equation of right? Is that okay?
So it's talking about it is
Okay, so now you have what was the square root of -2. Not real numbers, right? Numbers that make that numerator 0, aren't they? So if we have x is numerator 0 and the numerator is never 0, we don't have any x.
Okay, so these are right.
How's it going over here? Any sticking points? Yeah, confused, right? So I was just talking about that figures above, right? If we have an x-intercept, then what do we think? Well, that has a point where the function is if our function of maintenance is defined by a fraction, then
Looked at it, no, I know, there's just some ways.
X squared plus 2 equals 0.
Don't say.
I feel like it's
Yeah,
I'm gonna ask you about it.
Oh, yeah.
exactly. You can't do the square root of negative. We have an
Not
x-intercept
without
function
TI.
value is 0. Subject value is 0. The numerator is 0.
What is
Never. So,
I would've got one.
Okay, so we're on trying to find behavior.
okay.
So we got -2, we're just trying to figure out where
But I did get it.
here to be able to figure out the behavior.
So, basically what we're gonna do here is...
Yeah.
Okay, so...
No, it's harder to
Okay, if we're doing the asymptote or negative 3. Okay, what we want to do is rewrite it as x squared plus 2 divided by x minus 1 all times 1 over x plus 2. Right? So, in this case, the multiplicity of the 0 is 1. So we know where the m is positive. Now, we just need to figure out n of a over q of a. Whether it's positive or negative.
Because the bottom.
So to do that, we're just going to plug in, in this case is -2, we're going to plug it in here. So to get n of a
But I don't know what
over q of a, it's going to be what we get when we plug in the 0, which is -2. So we plug in -2, we get -2 squared plus 2 divided by -2 minus 1. Numerator is 4. Denominator is -3. So, what do we think? N of a over q of a, is it positive or negative? It's negative, right? So, we know we have this, and we have this. So the behavior is going to look like that.
Okay.
So that's what I'm going to draw here. So we have our horizontal. We can't cross the right. We know we should be above it on the left side of -2. This here is something like this here. Yes.
Okay, so we're gonna have like 4. I guess.
Well, next up, we're going to have to determine what happens if we have to over here. This or
Maybe I'll look at
like that.
Wait, why did this come out that?
Like spoiler alert, we know that we're not going to go like this because you know we have to drop the x-axis. Yes. I think we're already determined we don't have any x-axis.
Exponent.
Not yet.
Not yet.
Okay, so to do X-Intercept, right, we want to think about whatever that X value is, that's what we're going to get to. So I want to know, when is this fraction equal to 0? If I have a fraction that equals 0, then the numerator is so let's try to solve the equation, right? X squared plus 2, that's the numerator. And we want over q of x. X squared plus 2 equals 0.
I mean, it's
I don't know what
So what do we conclude? There's no x. Yes, for rational function. Yes, exactly. The x-intercepts are going to be where the
Oh,
no, mine. I'll be right there.
no, we didn't. What else should we have done? No.
I know I'm going to go over by like a minute. Is that okay? If you have to leave, leave. But I want to go over this really quickly. To find the X-Intercepts, okay, that is going to be where is the function 0. If the function is 0, then the numerator must be 0. So we set this equal to 0. We get x squared equals -2. Not possible. Not possible means no x-ints. Step 2 is to find the Y-intercept. What do? I plug 0. If I plug 0, I get 2 on top, and on the denominator, I get 2 times -1, which is -2. So the Y-intercept is going to be at -1. To find the vertical asymptotes and behavior, I need to look at where is the denominator 0, which is going to happen when x equals -2 or x equals +1, right? So I have a vertical asymptote at -2, and I have a vertical asymptote at +1. And the behavior is going to be determined, okay, for the x equals -2 intercept, it's going to be determined by the odd power here, which is 1, and the sign of what I get when I plug in -2 to the rest of this rational expression, okay? Which in this case, it ended up being a behavior, I think, which looked something like this, yeah? Something like that. Okay, to find the horizontal asymptote, okay, all we have to do is take a look at the power of the numerator. It is 2. The power of the denominator is 2. You can go ahead and leave if you have to. So what happens is they're the same degree. So the horizontal asymptote will be whatever we get when we divide the leading coefficient of the first by the leading coefficient of the second, which is 1. So we get y equals 1. So we know we also have a horizontal asymptote at 1. Finally, the other vertical asymptote, I think we have down on this side and up on this side, if I'm not mistaken. And so if we want to complete the graph, we have the location where it touches the x-axis, touches the y-axis. It doesn't touch the x-axis ever, and we know the behavior on each side, so it looks something like this and like this on this side. And then, of course, on the bottom, we just connect these two pieces. Okay? We connect those two pieces. All right. So that's all for today. Thanks for your attention. I hope you enjoyed the group work. We're going to be doing more of that moving forward.